Hey there, students. In this clip, we're going to be going over some examples on how to find the derivative of inverse trig functions. So let's go ahead and write down the directions for the examples. So for number one, we're to find y prime where y is equal to the inverse cosine of the square root of 3 times t. Okay? All right, so this is an inverse cosine function derivative problem. So let's go ahead and write down what the formula is first, and then we're going to be applying it to this problem. So the derivative ddx of the inverse cosine of x is equal to negative 1 over the square root of 1 minus x squared. Okay? In this case, we're going to be using the chain rule, right? Since the variable here, the input function of the inverse cosine, the input is a function itself. Okay? So let's go ahead and do it. Let's refresh our memory on what the chain rule is. If y is equal to, let me use a different color here. If y is equal to f of u, then you remember that the derivative of y prime, is going to be f prime of u times u prime. Okay, so that's the chain rule. All right, so that's what we're going to be doing here. We have y is equal to the inverse cosine of roots 3 times t. Now, if we find the derivative, y prime, of the outer function holding the inner fixed, we are going to have 1, negative 1 over the square root, applying this formula here, 1 minus u squared, which is roots 3 times t squared. Okay? And then we're going to multiply that by the derivative of the inner function u prime, which is roots 3t prime. All right? Now let's go ahead and simplify this piece and then differentiate that. We'll have y prime equals negative 1 over the square root of, if you square this, you have 1 minus root 3 squared is 3t squared, times, now if you differentiate this, we can factor out root 3, and the derivative of t is just 1, okay? And then our final answer, y prime, is going to be negative root 3 divided by the square root of 1 minus 3t squared. All right, so there goes your final answer for the derivative of the inverse cosine of root 3 times. All right, let's take a look at question number 2. So for problem 2, we're going to find y prime where y is equal to 1 divided by the inverse cosine of 3x. Okay, so if you take a look at this function, we're going to be making use of the chain rule twice. This is the composition of a rational function, an inverse trig function, and a linear function. Okay, so we're going to be using the chain rule here. So let's take a look at the order of differentiation. If I can rewrite this, in order to avoid using the quotient rule, I can rewrite this function as y equals the arccosine or inverse cosine of 3x raised to the negative 1 power. Okay, so note this negative 1 right here is the inverse of cosine. It's not reciprocation. So if you write this as cosine 3x by reciprocating this function, that will be inaccurate. Okay, so this is the correct way of writing it. All right, so let's go over the the formulas we're going to be using for this problem, formulas. The outermost function, the reciprocal function, is a composite function, so we're going to be using ddx of u to the negative 1, okay? So that's going to be negative 1 u to the negative 2 du dx. Or it could be written as negative 1 over u squared du dx. So this du dx component just indicates that you're going to be doing the chain rule. All right, when we're done with the negative, with the reciprocal function or rational function, we're going to shift our attention to the inverse cosine function. So if we find the derivative, ddx of arccosine of u, I'm using u here because we're going to be using the chain rule, that is going to be -1 over the square root of 1 minus u squared du dx. All right, because this is a composite function too. And then lastly, we're going to be left with the linear function on the inside. That one we're just going to go ddx of 3x, which is just simply 3. Okay, so if we combine all these functions together and plug in the respective values of u, then we should get the derivative. All right, so let's go ahead and do it. So starting with this right here, y prime is going to be, let's see, -1. Let's shift this to the left a little bit. -1, applying the power rule to the outer function, -1 times the arccosine of 3x raised to the -2 power. Okay, so that's the first rule here, -1u to -2, or I could have written it as -1 over arccosine of 3x squared. Now we're going to shift our attention to the next composite function, arccosine of 3x. So that derivative, we're going to use this formula right here to do it. All right, so that one is going to be 1 times -1 over the square root of u squared, right? So square root of 1 minus u squared. U is 3x in this case, so it's going to be minus 3x squared. All right, so that's the second differentiation. And then lastly, the innermost function 3x, if you differentiate 3x, you're going to have 3. All right, so let's rewrite this in a nicer way, simplified form. So we're going to have y prime equals, in the numerator is going to be -1 times -1 times 3, which is +3. +3 divided by, in the denominator I'm going to have the arccosine of 3x raised to the second power times the square root of 1, and then when you square 3x squared, 1 minus 9x squared. All right, so there goes the derivative of the 1 over the arccosine of 3x. All right, let's take a look at question number 3. So for question 3, we're going to find the velocity function. Find the velocity function for the position function x of t equals the arcsecant of 4t to the 4th power. Okay, so remember, if you want to find the velocity given the position, you're going to just differentiate the position function once. All right, so v of t is basically x prime of t. So what this problem is doing is asking us to differentiate this function once. Okay, so v of t is going to be x prime of t, which is arcsecant of 4t to the 4th prime. All right, the derivative of that. All right, so let's look at the formulas we're going to use to find the derivative of this composite function. The outermost function is the arcsecant function. So it's arcsecant and is also a composite function, so we have to use a chain rule for that. So I'm going to use the formula ddx of arcsecant can also be written as secant to the -1 of u. U because the argument or the input of the arcsecant function is a function. So we have a composite situation here. So we're going to use arcsecant of u. So the derivative of this is 1 over the absolute value of u times the square root of u squared minus 1. And since we're using the chain rule, times du dx, basically the derivative of the inner function. Okay, and then when we're differentiating the inner function, we're basically going to be using using the power rule here. Let me just make sure yeah, so that's how it's going to be. But in this case, we're differentiating with respect to t, so let's be consistent with that. So d dt, since that's what we're looking for with respect to time, d dt du dt. All right, and then when we're doing the innermost function, we're going to be differentiating d dt of 4t to the fourth. And that one, for this one, we just use the power rule, and it's going to be 16 t to the third power. All right, you don't need the chain rule for the innermost one. So that's basically what we're going to have. If I multiply this by that and substitute the value of u into that, that will be what the derivative will be. Okay. All right, let's go ahead and apply to this function. So v of t, the velocity function, which is going to be the derivative of arcsecant. So the derivative of arcsecant using this formula is going to be 1 over the absolute value of 4t to the fourth, okay, times the square root of u squared minus 1, where u is 4t to the fourth. So it's going to be 4t to the fourth square minus 1. All right, so that's how it's going to be. All right. All right, and then we're going to differentiate the inner function, okay? Now we're going to differentiate the inner function. When we differentiate the inner function is 4t to the fourth. So basically we're going to apply the power here as we did over here. And then it's going to be times 16t to the third. All right, that's du dt. Okay, let's go ahead and simplify this a little bit more. Now let's examine this denominator right here. If you notice, we're taking the absolute value of an even power. Okay, if you're taking the absolute value of an even power, the absolute value sign is pointless, or it has no value, because the fourth power is going to ensure that this t is always going to be positive. So since that doesn't play any role, we can completely drop the absolute value bars. So let's put the numerator first, 16t to the third over, now in the denominator, absolute value 4 is 4, and then t to the fourth because of the even power, all right? And then that times the square root of 4t to the fourth square is going to give us 16. If you use the product of a power property of exponents, you square the 4, which is 16, and when you square t to the 4, you have t to the 8 minus 1. All right? If you notice, we can simplify the numerator. If we divide top and bottom by the GCF, which is 4t to the third power. So we can divide the top and bottom by 4t to the third. Okay? If I do that, my final answer, on the top I'll be left with 4. And then in the bottom, I'll be left with t, is t by itself, t times the square root of 16t to the 8th minus 1. So this is basically your velocity function given this position function x of t equals the arcsecant of 4t to the fourth power. So there you have it. We're to find the acceleration function. The acceleration function where the velocity function v of t is equal to the inverse cosecant of 3e to the 2t. Okay, so there you have that's the velocity function. Okay, so in order to get the acceleration, a prime of t, a of t, that's simply the derivative of the velocity function v prime of t. Okay, so what we're doing in essence is we're going to be looking for the derivative of the inverse cosecant of 3e to the 2t. Okay, so we're going to be using the derivative of the inverse cosecant function and also the exponential function by using chain rule here. So let's first of all determine what the formula is for the derivative of the inverse cosecant function. So d dx of inverse cosecant x is equal to -1. It's just like the secant function, just the opposite, over the absolute value of x times the square root of x squared minus 1. Alright, so let's go ahead and apply that here. Acceleration function a of t is equal to -1 over the absolute value of x. In this case, since we have a composite function, x is going to be the input function, which is 3e to the 2t. So it's going to be absolute value of 3e to the 2t times the square root of 3e to the 2t squared minus 1. Okay, so that's the derivative of the outer function, and then if you differentiate 3e to the 2t, you're going to have to use the chain rule here again. If you differentiate 3e to the 2t, you're going to have 3e to the 2t, and then when you differentiate the innermost function, which is 2t, you're just going to have 2. Alright, so let's go ahead and simplify that. If you simplify that, we're going to have in the numerator 6e to the 2t, and in the denominator that's divided by, let's see what's divided by. Now if you examine the exponential function 3e to the 2t, you know what your exponential function looks like, right? What the graph of the exponential function looks like. So if you have 3e to the 2t, what's going to happen is that we're just going to have a dilation along the y-axis. Is going to stretch it, but it's going to look something like this, your exponential function. All right. So if you have an exponential function that looks something like this, what does it tell you about the sign? 3e to the 2t is always positive, so this absolute value can be dropped. So we can just express this as 3e to the 2t. All right, because of that's the range of the exponential function is positive. That times the square root of, and if you expand this, you're going to have 9e to the 4t minus 1. Okay. Now, you notice we can reduce this. 3 goes here once, 3 goes here twice, and then the e to the 2t's divide out. Alright, let's not forget the negative over there. So your final answer is going to be -2 over the square root of 9e to the 4t minus 1. Alright, so that is your acceleration function. Alright, let's take a look at the last example. Example 5. Number 5. For number 5, we're going to find y prime. Find y prime where y is equal to the inverse tan of 1 over x, the inverse tan of 1 over x, plus the inverse tan of cotangent x. Okay, so we're going to be using the formula for the derivative of the inverse tan and cotangent function. So before we use them, well, before we find the derivative, how about we state what the formulas are for the derivative of this inverse trig functions. Alright, so let's start with tan. The derivative of inverse tan x is equal to 1 over 1 plus x squared. Okay, and the derivative of inverse cotangent x is very similar to the inverse tan. The only difference is that it's the opposite. Okay, -1 over 1 plus x squared. Okay, so these are the two formulas we're going to be using here. In the case of inverse tan, we're going to be using the chain rule. Okay, so y prime is differentiate tan first. The derivative of tan is going to be 1 over 1 plus, this is the x, or we're basically using u here. We're going to be using the chain rule, so we can call this u. So differentiate the outside whole and the inner fixed. So if I plug the inner function right here, 1 over x squared, that's for this x, times the derivative of 1 over x. We can look at 1 over x as being equal to x to the negative 1, right? So if you differentiate, let's do that on the side so I don't mess up the work. So if I want to differentiate 1 over x, is the same thing as x to the negative 1 prime. And if I differentiate x to the negative 1, it's going to be negative x to the negative 2, which is equal to negative 1 over x squared. Okay, so that's the derivative of this inner function right there. So I'm going to multiply this by negative 1 over x squared. Plus, now if I differentiate inverse cotangent using this formula, it's going to be times negative 1 over 1 plus x squared. All right, let's go ahead and simplify this expression. So what we're going to have is y prime equals, now if I'm going to distribute this x squared to these terms right here, so I have negative 1 in the denominator. X squared times 1 is x squared. And then this one is going to be plus x squared over x squared. Because when you square 1 is just 1, 1 times x squared is x squared. And then when you square x squared, just x squared on the bottom. So we have that. And then on the right side, we'll have minus, because minus times plus, minus 1 over 1 plus x squared. And simplified further, we're going to have y prime equals negative 1 over, if we use the commutative property of equality, I can rewrite this as x squared over x squared is 1, so 1 plus x squared minus 1 over 1 plus x squared. So this is simply going to be negative 2 over 1 plus x squared. So that's our final answer. Y prime equals negative 2 over 1 plus x squared. All right, so there you have it. So thanks so much for taking the time to watch this presentation. You can feel free to subscribe to my channel or post a comment to let me know what you think. Click like if you like this video, and feel free to share it with your friends via your respective social networking program. Thanks again for watching, and have